It's time for another physics take-home lab. Today's lab is the construction of a balance scale for massing an object, basically, or to obtain an object's mass, which makes use of the equilibrium condition imposed by Newton's first law as applied to both translation and rotation. All right. In your lab handout, the theory is fairly well described for this, but I'll write the two conditions. You basically need to have, on the one hand, that the acceleration of the system is 0, and on the other hand, that the angular acceleration of the system is 0. And in order for that to occur, this right here by Newton's first law says that the forces acting on your system or object must all balance. This one says that the torques acting on your system or object must all balance. And it should be noted that torque is defined by this relationship R cross F. Basically means that the magnitude of the torque is R times F times sine theta. And I will draw the attendant diagram over here somewhere. You might have, for example, a system like a wrench. So you have a wrench which is being used to apply some force, some torque on a nut. And so you apply some force out here on the end of the wrench, F, and the nut is pivoting about some location here, which we can mark off using an R. Okay, so the torque is this distance times this force times the sine of the angle that goes between the two of them. You could, for example, push directly up, in which case this sine term goes to 0, goes to 1. Or you could be pushing off at some angle like this. And so you have sort of a perpendicular component, which is F. This right here is theta, and that also makes this theta. So your perpendicular force is this force F times the sine of theta. Okay. So that's the basic background. We're looking to balance torque, we're looking to balance force. Torques are given by this quantity, which is explained by this diagram. Now, what about the lab itself? We're going to look at how to do the actual lab here, and then I will make an addition to the video that shows how to do some of the calculations. The first step of this lab, and this is a step that you have to do before beginning the lab, and you kind of have to do in the lab on campus, or else be using a standardized part, is that you have your calibration weight. And we're basically going to use these washers as our calibration weights, but you have to know what the mass of your calibration weight is. Okay, so step 1 is get the mass of the calibration weight. This mass that's showing is actually in kilograms, so this comes to 4.2 grams. In addition to the calibration weight, you will need a couple of other parts. Specifically, you're supposed to have an unknown mass that is fairly light, comparable to maybe a few times your calibration weight. And you're supposed to have one that is a little heavier, comparable to several times your calibration weight. You don't know what these two objects have as their mass, however. They're unknown objects. Your goal is to get the mass of the unknown objects in this lab. In addition to this, you will need, and I will set this up, basically some sort of a lever arm. I recommend a simple paint stick like this because they're nice and flat, they have known length and so on. You also need something to measure the length of the paint stick. This could be a ruler, could be a tape measure, could be anything. For that matter, if you have a rigid ruler, and this is unfortunately not rigid enough for the experiment, but if you have a rigid ruler, then you can combine these two things into one object and just use your ruler. In addition to that, you will need something to place your lever arm on, basically a fulcrum. And what I've chosen as my fulcrum is basically one of these little L-shaped brackets. It works like this, so set on its side. You can actually also get it to work when set like this, as long as it is not overbalanced, which for the weights used here, this one shouldn't be. But you don't need to get the big heavy version. They make them that are like maybe this thick only. Okay, so that's it for equipment. That's what you'll need equipment-wise. You need your calibration weight. You know the mass of your calibration weight. You need a mystery weight of some unknown mass. You need a second mystery weight of some larger unknown mass. I don't want you to be able to just write down the numbers that I've obtained and say I did the lab. You need to do the lab yourself. So I've given you the parts to find them. They are not the same things that I'm using today for that reason. Alright, now that you have all your equipment, it is time to walk through how to do the lab itself. So we set up our fulcrum. The first thing we have to do is determine where the center of gravity is for our lever arm, for our stick, in other words. The way that you do that is you set the stick on the fulcrum. You basically move it back and forth until you find the location at which it balances. It is now balanced on the fulcrum. And so once you have a balance point, not a bad idea to maybe mark that point. So it balances when it's placed about here. And then you need to measure where that location is using your tape measure or ruler or what have you. So this right here appears to be at the location of about, well, if we take this end over here to be 0 centimeters, then this is at the 17, looks like 17.5, and then you could estimate maybe 17.55 centimeters is the rough location, the center of gravity for this. Next step, now that we have that location of the center of gravity, is that we need to get the mass of this stick. So we don't know what the mass is, but we do know what the mass of our calibration weight is. You'll recall that we got it earlier as 4.2 grams. And what we do is we find a location to place the calibration weight. Maybe we place it midway between this mark and the end, for example, would be acceptable. So this right here, the end was 0. Maybe we place it 10 centimeters from the end like this. And then what we do is we place the stick back on the fulcrum and we move it back and forth until the system is again balanced. And so this is roughly balanced. We might actually move it slightly in this direction to get a slightly better balance. The amount of moving that we do with this stick gives us an estimate of the uncertainty, by the way, in the position. So I might make another mark on here that shows where the balance point is when the mass is located at 10 centimeters. And then I would write that into my table. So this balance point is actually right at 16 centimeters. And from these you will be able to calculate what is the mass of the stick. Now that you know where the center of mass is for this stick, and you know what the actual mass of the stick is, the next step is to use it to get the mass of your unknown objects. Alright, so let's start with the smaller of the two unknown objects. The basic process is that you place your calibration weight somewhere on the stick, and you should even measure where on the stick the calibration weight is located. It turns out that this is centered right around 1.2 centimeters from the end of the stick. So then you place your system back on the pivot, and then you place your unknown weight on the stick and you move it until the system is balanced. And there my system is balanced. Okay, so one thing you should know about this, I have deliberately set it up so that the center of gravity for the stick itself is over the top of the pivot point. It's possible to find a location, basically it's possible to move the stick so that it's balanced, and move this weight and this weight so that it's balanced without having the pivot and the center of gravity in the same location. But if you can put the center of gravity in the same location as the pivot, it's actually an easier calculation at the end to do it that way, as we'll see in a moment. You will need to measure where this unknown weight is relative to the end. It happens to be at the 23.9 centimeter mark. Now you basically repeat this process for the second unknown weight. However, you will find that to get the second unknown weight balanced and to have at least a few centimeters from the pivot point, that it is actually becomes necessary to move the stick so that the weight of the stick is helping to counter the large weight of the unknown mass. So you move it around until it's balanced around here. And then you measure where everything is located. So again, the calibration weight is at 1.2 centimeters. The pivot point is now right at 20 centimeters, and the unknown weights are at 23 centimeters. Now that you've seen how to do the lab experiment, it's time to walk through how to do the calculations that go with this lab experiment. You have filled out your data table for both part 1 and part 2, and now you're left with questions like how to figure out the stick's mass and then how to figure out the mystery masses. Okay, so we'll begin with the stick mass itself. The setup for that is something like this. You have a fulcrum, you have the stick itself, just like this, and then you have a calibration weight which has been placed somewhere on the stick. So we could say that there's a center of gravity. We'll put a little X here, center of gravity for the stick. And basically what you have is you have the force downward from the stick. F stick would be mass of stick times G. You have the force downward here from your calibration weight, mass calibration times G. That would be like the force from the calibration weight. And then there's also an upward force over here that is from the fulcrum. We'll call this F full for fulcrum. And what we're looking for is the stick mass, or the stick's mass, which would be m sub s in these equations. Alright, so basically what we are going to do here is we're going to make use of the conditions for equilibrium. Oops, I may have moved this up a little too much. Just want to move it to about right here. We want to make use of the conditions for equilibrium, which are basically described in these equations. You basically are using tau equals r cross f, which comes to r times f times sine theta, and you want the sum of torques to equal 0. Those are that will satisfy the equilibrium. Okay, so we are basically doing this part right here, the mass of the lever arm, or of the stick. In order to solve this, we have to pick an axis of rotation. So I'm going to pick my axis of rotation to be right here where the pivot is located. So this right here we can mark as axis of rotation. So all distances must be calculated with respect to this axis. Now, our data table that we've made here tells us where we put the pivot point, which is where we've chosen the axis of rotation. This is the 16 centimeter mark. Okay, and then we have, in addition to these, the stick center of gravity location and the calibration weight location. Okay, so the first thing that we got to do now that we've picked an axis of rotation, is determine the values of r for these two. So this would be r for the calibration weight. This right here would be r for the center of gravity for the stick. Okay, and this right here is basically your x equals 0 location. All right, so this right here, x calibration, is 10 centimeters. The axis of rotation, we'll call that x sub r, happens to also be x sub fulcrum. That was our 16.0 centimeters. And then this right here, x stick or x center of gravity, we found was 17.55 centimeters. Okay, so to get r sub I, comma, and then choice of axis, we might say P or whatever, or fulcrum, is given by basically the difference in position. So it'd be essentially x sub I minus x sub ful. Okay, so we've chosen this location of the fulcrum to be our axis of rotation. What this is basically telling us is that on the one hand we have we have r for the calibration weight relative to the fulcrum, and that is essentially 10.0 centimeters minus 16.0 centimeters, and so you get negative 6.0 centimeters for that. You can make it positive if you'd like, because the sign conventions are going to come out of the direction that torque is acting in. So in some sense we can say that it's really this. Okay, and so this ends up just being 6.0 centimeters. And then likewise, r for the center of gravity, or r for the stick if you will, would be 17.55 centimeters minus 16.0 centimeters. Okay, and you're going to take an absolute value, but it's going to be positive anyway. You end up with 1.55 centimeters. And again, arguably this digit is maybe an extra digit given that everything else is only to the tens place. So we might even say that this is actually 1.6 centimeters. Okay, now the next step is, now that we've found the r's, we basically can do sum of torques is equal to 0. And for what it's worth, there's this other force as well. We could do r sub fulcrum relative to fulcrum, and that's just subtracting this distance from itself, so it is by definition 0. Alright, so the next step is basically that we want to add all of the torques together and get 0. Okay, so this is the ultimate equation that we're solving. This sum of torques basically just is essentially r sub c fulcrum crossed with f sub c, and then r sub f fulcrum crossed with f from the fulcrum, and then r for the center of gravity, or r sub stick, crossed with f for the stick. Okay, and this one right here we already established was 0, so this whole term basically is going to go away. These cross products basically just mean multiply the distance, multiply the force, and then multiply the sine of the angle. But keep in mind that we can bring out these angles are all basically 90 degrees, but this 90 degrees and this 90 degrees are not, they don't give the same result. The two torques are in opposite directions. And so, in some sense, if this is plus 90 degrees, then this is equivalent to minus 90 degrees, or vice versa. Okay, so this right here could be equivalent to saying that R sub C fulcrum times F sub C minus R sub S F sub S is equal to 0. Now we basically just plug our numbers in. We found them up here. What you basically have is something like, okay, we need mg for each of these. So R sub C fulcrum times mc times g minus rc minus rs, excuse me, fulcrum times ms times g is 0. Alright, and so there's a g term in both, so we can get rid of those. We're trying to solve ultimately for this guy right here, the mass of the stick. So let's go ahead and do that before we plug our numbers in. This says that the mass of the stick is going to be the ratio of these two radii for RC and for RS times the mass of the calibration. Okay, so now we'll plug in our numbers again. MS, so RC, that was 6 centimeters, so we have 6.0 centimeters. We're dividing that by basically 1.6 centimeters, and then we're multiplying by MC. So if we pull this guy back up to look up what MC was, that was your 4.2 grams. And so we come back over here, we plug in our 4.2 grams. All right, and then you basically throw all those numbers into a calculator. So that would be 6 divided by 1.6 times 4.2. What you end up getting is 15.75. So 15.75 grams. Probably, again, we should round this. I think that you could get it really to the nearest whole gram if you're following significant figure rules based on what we've done here. When you do the experiment yourself, you may actually be able to get one more digit because stuff may be a little farther, or you may be able to get this level of precision, etc. But with the numbers I've written down, this is 16 grams. All right, so we've just basically shown our work for this part, and we've come up with a mass 16 grams here. Again, the stick's mass shows up down here. It also says 16 grams in both cases. The other parts here, this one right here essentially says figure out what the upward force exerted by the fulcrum is. To do that, all you have to do is apply the other condition for equilibrium. So let's do that real quick. That basically just says sum of forces must be 0. Okay, and so that means that your mass of your stick times g, which is downward, so we'll put a negative sign, plus your mass of your calibration weight times g, which is also down, so again negative sign, plus the force from the fulcrum, add to 0. Okay, and so the force from the fulcrum must be the sum of these two masses, mass of stick plus mass of calibration weight, times g. If we want this in newtons, then these actually need to be in kilograms. So what you end up with is 0.0042 kilograms plus 16 kilograms times 9.8 meters per second squared. So your force from your fulcrum, we've got to plug these guys into our calculator. So let's see, plus 4.2 times 9.8, you get about 196. This, sorry, should be 0.016 kilograms. All right, so you plug all those in, you end up getting 0.20 newtons. Okay, that doesn't go anywhere on the table, but it does answer this question. And then the other two parts are to verify that choice of axis does not affect your answers here. In other words, you get the same mass for the stick and the same upward force for the lever arm, regardless of axis choice. So to show that, you basically would bring back your stick again. So I'm going to go ahead and redraw the stick. So you have your stick like this. You've got your pivot or your fulcrum point. You got your calibration mass. You got your center of mass over here somewhere. Okay, so this is still known. This is still your 4.2 grams. Determine ms again, or you could show, knowing ms, that all the forces still add to zero and all the torques add to zero. Either way works. But now we pick our axis of rotation to be here. So given that r sub I comma, this is like the zero end, this just would be x sub I minus x sub 0, but x sub 0 by definition is 0, so you just end up with the x sub i's. So this right here is 10 centimeters. This right here is your 16 centimeters. And this right here is your 17.6 centimeters. All right. And so you'd basically repeat the calculation from above using these information to show that the sum of torques is still 0. Okay, and so you'd now have to figure out what the torques are about this axis for each one of these things. Rule of thumb, if the torque makes the thing want to rotate in a counterclockwise direction about your axis of rotation, then it's positive. If it wants to go clockwise, then it's negative. So your sum of torques would really look like force from the fulcrum times r from the fulcrum minus force from the calibration weight times r from the calibration weight minus force from the stick times the distance to the stick center of mass. All right. So you have all these numbers from above. You just are verifying whether or not they add up to 0 or very nearly 0 with some round off error. Okay, and then you can repeat it again with the other end of the stick being chosen. And for that one, you might use something like r sub I comma end is just x sub I minus length of stick. Okay, so that gets you everything for part 1. Before we can continue on to determining the mass of the two unknown objects, we need a word from our sponsor. Today's video has been sponsored by an apple. Not just any apple, specifically this apple. They say an apple a day can keep the doctor away. Not only that, but they are delicious. Product of the United States. Keep jobs here in America. So go out and buy an apple, specifically one like this, to keep your doctors at bay. Now that we've obtained the mass for the stick, we can determine the mass of each of the two mystery objects, and we're going to do each of those in turn. So we'll start with mystery object number 1. You'll recall that we placed the fulcrum, the pivot, at the same place as the center of mass for the stick for this one. So this calculation is actually pretty straightforward. We're basically doing determine the mass of the smaller mystery object. And it is a very straightforward calculation. In fact, it's pretty similar to the one that we've already done. If we draw ourselves a diagram here, here's our stick, here is the fulcrum point, here also is the center of mass for the stick. So this would be like F stick. This could be F from the fulcrum, and then we have our calibration weight right here. So this is F calibration. We have our mystery object number 1 here. Call that F1. So that's M1G. This is MCG, and this right here is MSG, not to be confused with the food seasoning, if you want to call it a food seasoning. Now, as I said, we placed our pivot point location, our fulcrum location, at the same place as the stick's center of gravity. The best decision, therefore, for a choice of axis here, since this choice is basically left open to us, would be to choose our axis of rotation to be actually right here. Okay, so if this is our axis of rotation, then it follows that this right here would be R sub C, and this right here would be R1. Okay, and it basically means R sub I, comma, I guess we could use S for stick or center of mass, and that will just be X sub I minus X sub S, and again you can take an absolute value. Alright, so again we have 4 objects. We have R sub C, that one. We look over here, we see that we place the calibration weight at 1.2 centimeters this time. So we'd basically be using 1.2 centimeters minus 17.6 centimeters. Take absolute value. This is 16.4 centimeters. All right, our fulcrum and our stick both end up being 0 because they're both at the axis of rotation, and then R1 ends up being the position of the unknown weight, which is listed right here as 23.9 centimeters. Okay, so we have 23.9 8.9 centimeters minus 17.6 centimeters. Oops. Alright, so this should be something like 6.3 centimeters. Alright, now that we've found those, we turn to the sum of torques being 0. Alright, and so this basically is saying that R sub C comma S times MC times G, and that's in the counterclockwise direction, so that's the positive one. Basically wants to rotate like this. This one wants us to rotate like this. So that plus, these two are both 0, so you'd have RSS MSG, but this is 0. You'd have R fulcrum S times F fulcrum. We don't know F fulcrum, by the way, because we've changed how much weight it's having to hold up, but it's okay. It's still, the term is still 0 because of this distance is 0. And then this one being clockwise, we would have R sub 1 times M1 times G, and all that goes to 0. Okay, so these two terms have vanished. We are solving for this term right here. If we subtract from both sides, or add to both sides, excuse me, and then divide by R times G, you get M1 is equal to R sub C S. This is R sub 1 S. So R sub CS over R sub 1 S times M sub C. So same basic equation that we had before when we were figuring out the mass of the stick. And if we're being really thorough here, these are comma S's. So these terms right here are the things we found up here. So this right here says that M1 must be 16.4 centimeters divided by 6.3 centimeters times 4.2 grams. All right. So plug these into the calculator, and what do we get? We get 16.4 divided by 6.3 times 4.2. That's actually about 10.9 grams. So again, we only have in this video two significant figures to work with because of this term, and really because of this term as well. So this we would write as 11 grams. Alright, and we can come to our data table and put in an 11 here. Alright, so we just answered this question. It wants to know what's the upward force from the fulcrum. Really that's pertinent for the larger one, but you could in principle do that for the smaller mass as well. You do it the same way as we did before, which is that you say that the sum of forces acting on the stick must now be equal. Okay, so you'd say sum of forces is equal to 0. And downward forces, you have M1 times G, you have MC times G, you have MS times G, and then the upward force is your force of your fulcrum. That's equal to 0. So move all of this stuff over to here, and you have that the force of the fulcrum is M1 plus MC plus MS times G. And so M1 is, we just found, was 11 grams. MC was 4.2 grams. MS was what we found before, was 16 grams. All right here, the mass of the stick. Okay. We have to convert that to kilograms, so we have 1 kilogram per 1,000 grams, and then times 9.8 newtons per kilogram. Alright, and so that gets you your upward force for the fulcrum, so 11 plus 16 plus 4.2, so that's 31.2, although we only have to the nearest whole number, so really 31. And that times 9.8, and that divided by 1,000 gets you 0.30576. So F fulcrum 0.30576 newtons. With significant figures, that becomes 0.31 newtons. Alright, so same as the process that we used before. Okay, so now we're ready to do the other unknown mass, the other mystery object. Now this other mystery object, you'll recall we had to actually move the pivot point off of the center of mass of the stick. So our new diagram would now look more like this. We have our stick like this. We had our calibration mass, so m sub c times g, this is your f sub c. We had our center of gravity for the stick, so ms times g for f sub s. We had our pivot point, putting a force upward like this, F fulcrum. And then we had our unknown mystery mass number 2, which is over here. So this would be F sub 2 is m2 times g. Alright, so we can no longer just say the axis of rotation is the same as the fulcrum and the stick. We now have to make some decision for where we want the axis of rotation to be. And again, the force from the fulcrum has changed again because we've changed how much total weight it's holding up. It's the only upward force. So since it is an unknown, probably the best choice would be to pick this as your axis of rotation yet again. Alright, and basically that means that you now have, we could call this R sub c, that goes like this. We have R sub s, and we have R sub 2. And these are all with respect to the axis of rotation. So R sub I, comma, fulcrum. So these are all comma, fulcrum, comma, fulcrum, comma, fulcrum. Okay, so these R sub i's are now x sub I minus x fulcrum. And again, take an absolute value. So again, you're going to have 4 results. Now we've moved the fulcrum to the 20 centimeter mark. The pivot point location of the fulcrum is at 20 centimeters. Okay, so that means that this right here, the calibration weight, x sub c, is 1.2 centimeters minus 20 centimeters. Again, taking an absolute value, that gives us 18.8 centimeters. All right, and our, oops, this is r, not s, not x. Our r sub s, this was at 17.6 centimeters and 20 centimeters. So this is 2.4 centimeters. Our fulcrum position is just 0 because it's at the axis of rotation. And our position for the other mystery mass was at 23 centimeters. And again, if you're not remembering where I got that from, we're just looking it up. It's mystery object 2. Where is it located? It's 23 centimeters. So that's where that's coming from. So this ends up being 3.0 centimeters. Okay, now that we've done that, we now basically can go back to our sum of torques equals 0 equation, and we look at each torque about this axis and which direction it's in. This one right here would want to go this way. This one right here is this way. This one right here is this way. So this and this are counterclockwise. So we have essentially R sub C fulcrum times MC times G. And we have RS fulcrum MS times G. And then this term is a 0 term, but basically R fulcrum times F fulcrum. This is the 0 term. And then this is in the clockwise direction, so we would have R, this is a 2, not an S, R2 comma fulcrum times M2 times G is 0. We're solving for M2, so M2. Now we have two terms to move over and then divide. So we end up with R sub C fulcrum times M sub C plus R sub S fulcrum times M sub S, and then that's divided by R2. Okay, so plugging numbers in, you end up with 18.8 centimeters times 4.2 grams. I'm going to abbreviate that as GR. And then 2.4 centimeters times 16 grams. And then that is being divided by R2, which is 3.0 centimeters. Okay, so plug everything into the calculator. What you end up with is 18.8 times 4.2 plus 2.4 times 16 divided by 3. What you get is 39.12 grams. So mystery mass 2 is about 39 grams. So now we can write in that mass into our table. We have the mass of both mystery objects, therefore we have all the masses. At this point, you're supposed to actually go and get the upward force from the fulcrum using this second mystery mass. So it's the same calculation that I've done for you twice already, but now with the mystery mass number 2 used rather than mystery mass 1. And then after that, you again go and verify that the choice of axis doesn't affect the condition that the torques must balance, this condition here. So again, you pick what happens if you've picked each of the two ends of the stick, and determine the total torque about each end of the stick, and you should find that it's still 0. And again, you're using the known values for the masses of everything and the force from the fulcrum. And so it's a repeat of the previous calculation that I did of that sort when we were just finding the mass of the stick. And so once you've done that, the last thing is to basically write your conclusion from this experiment. Maybe go about describing how such a thing like a triple beam balance or the balance scale at a doctor's office, how do these things work? Is one idea for your conclusion. You could also discuss how you could make the experiment better. How can you add precision to it? What would change if instead of using a triangular or sort of point-like pivot, what would happen if we used like a block instead? And once you've done all that, you basically have finished this lab. So hopefully this video helps you to complete the lab at home. And as always, if you have questions, you can send me your questions and I'll do my best to answer them. So good luck.